All right, so we're picking up where we where we left off last time. And so last time we introduced numerical simulation of dynamical systems, how you would do this in a spreadsheet, kind of if you had to do a dynamical simulation by hand. And I gave you an assignment, D1, that it's due Sunday, but in this lecture, we're basically going to do the assignment or tell you how to do the assignment in its entirety, so that you kind of have an assignment where you know the solutions. And then at the end of this, then you'll have a new assignment that will allow you to do something the exact same way, but in a different system other than the bacterial system, so that you'll have an opportunity to practice something you know how to do and then transfer that to use the exact same methods to do something slightly new. And then what we're looking at forward for next week is we're going to learn how to do these dynamical simulations in VinSim and InsightMaker. And so next week, you're basically going to do the exact same assignment that'll be assigned today, but instead of doing it in a spreadsheet, you're going to do it inside VinSim or InsightMaker. So that's how everything kind of connects. All right, so let's kind of go back to then last time to see where we were. So in last time, we handled the problem of simulating population dynamics, and we stuck with bacterial population dynamics because they're simple for now, because we can just think of every bacteria reproducing asexually, so they're just sort of clonal. So we don't have to worry about maintaining, this type of a population and this type of population have to find each other and all that. They just, depending on how many bacteria are there, you can kind of predict how many bacteria are going to be there a little bit later. And we said, in order to sort of model this system, we are going to think about it like we think about a bank. Because in a bank, you also have a similar set of a similar system where you've got dollars in the bank, and those dollars magically turn into dollars and fraction of dollars. And that process we refer to as interest. And so we are converting bacteria into a bank. And so we're going to have to find a way to turn bacteria into a system that we can model the same way we model interest accumulating in a bank. And through that process, we will learn how to model any dynamical system that way. So basically, every single dynamical system you can think of, watching a baseball fly through the air, trying to figure out where its position will be at every step of time, watching the planets circle, thinking about how populations change in a city, how they grow, collapse, or grow, and then reach a plateau and then collapse. All of those dynamical processes, we're going to realize that if we cut them up into small enough segments of time, whereas we can assume that nothing changes during that segment of time, but whatever the state is during that segment of time tells us where things are going to be at the next segment of time, then we can simulate anything. And so long as you can, every single dynamical system, if you look at it at a small enough slice of time, looks like it's constant, looks like it's not changing. So every single dynamical system, if you zoom in on it, looks like a bank. And so how does a bank work? Well, at a bank, at the beginning of the year, you start with a certain amount of money. Every dollar in your bank account. I'm sorry, is there a question? All right, sorry. Okay, so at the end of every year, then you get whatever amount of money you had at the beginning of that year, plus some fraction of every dollar that was in the bank account. You don't get to spend that fraction of a dollar till the end of the compounding period. For simplicity, we're saying till the end of the year, but it's as if it's always potentially there. So it's like the whole year, you've got this potential slice of a dollar that you could use, and you don't actually get allowed to use until the next year. So if we put that on a timeline, we start out with a certain initial balance. Every dollar that is in our account becomes a dollar plus a fraction. And at the next time period, that little fraction that we earned during that first year becomes available for us to use. And once it becomes available for us to use, it starts generating its own little fraction in the bank. And those new fractions, the fraction from your old dollar and the fraction of your new dollar, aren't available to you in that second year, but they will be available to you in that third year. And each one of those that are now available starts generating their own interest, and so on and so forth. This is how we think of compound interest at the bank. And it's a very simple model. It's easy for us to calculate. All you need to know is how much money you had at the beginning of the year, and then you can figure out how much money you'll have in the next year. We need something that simple for systems like the bacterial system. So we need to figure out how to turn the bacterial system into the bank example. And so where are the similarities and differences? Well, in the bacterial system, you start out with a single bacterium. And then after some waiting time, which I'm calling W, so W could be 5 minutes, for example. So that's why I say W time units. So the time unit here might be minutes and W might be 5. Then on average, every bacteria you have at the beginning or right after it's reproduced takes about 5 minutes until it reproduces again. So it's a little bit different than the bank account example, because it's not like generating fractional bacteria every year. It's generating a whole bacteria, however long it takes to generate a whole bacteria. So in our bacterial example, you've got 1 bacteria, it becomes 2, and then in some time, maybe less than the average time, then every one of those bacteria will become 2 again. And then maybe again, every one of those bacteria will become 2 again, and sometime less than the average. But then you might have some time that if you zoom in on one of those bacteria, it might take it more than the average in order for it to generate a new bacteria. And then maybe a couple other times it'll take more than the average. But on average, every bacterium after it reproduces takes about W time units to reproduce. So again, this in some ways looks somewhat similar to our bank account, but it would be almost as if we say you don't get to use your interest until your $1 accumulates enough interest to become 2 whole dollars. That's kind of like if you've got an Amazon Associates account, or you've written an article for Medium or something like that, where they're saying that we're not actually going to pay you until your credit in your Medium account, your Google AdSense account or whatever, hits $20. So you don't actually get to use that $20 until it's full $20 are there, and then suddenly you get all the $20. That would be kind of a weird bank to be a part of, because we can cut dollars up. But it would still not be that different in the long term. Like if you zoomed out 100 years, then a bank that operates like the banks we understand, or bank that operates like that other weird bank where you have to wait for you get a full dollar to use it, wouldn't seem that different. And so that's what we're trying to do, is to find a connection between those two sort of interest strategies. And so what we're going to do is we're going to turn the bacterium of the real world into the bacteria of the banking world. And if we do that at small enough time scales, then this approximation will be good. And so if our compounding interest periods are so small that there is very little likelihood that a bacteria would reproduce during those compounding periods, then this banking approximation is going to work. So the idea here is we're assuming that every bacterium has a certain flow rate, and it's constantly pouring out fractional bacteria, and that fractional bacteria accumulate per bacteria at 1/W. And so this would mean that if you waited a whole W time units, then the 1 bacteria would pour out a whole second bacteria. And if you knew that you had 15 bacteria, then 15 times 1/W would be the net flow rate coming out of all of your population of bacteria pouring into partial bacteria. And so, but we're not going to wait the full W time units. We're only going to wait our tiny little banking compounding period of DT time units. So then we can say for every 1 bacteria, it is pouring out at a rate of 1/W. And we are going to pretend that the stuff that it produces doesn't start producing its own new flows until after the DT time units. And that just makes it easier for the bookkeeping. So for this tiny little DT time unit, where we're assuming that DT is much smaller than W, and that sort of guarantees that in our compounding period, no bacteria are going to reproduce, then we know that, well, if it's flowing out at a rate of 1/W, then after the DT time units, then we are going to have a total of DT divided by W, or DT times 1/W, that would that is going to be available for the next generation of bacteria to add to their numbers. There's a question here in the chat. Would flow of new bacteria be the same as births? Yes, this is our approximation of births. Births are kind of like the top up here. So we know that when someone's born, then, or when a bacteria is born, you get a whole bacteria. We can't, it's not easy for us to simulate a whole bacteria because that's like this weird event that happens randomly and stuff like that. So we are going to simplify and look at the population at kind of a mile-high view, and looking down at the population, then we kind of see the kind of average. And on average, you get, after a small amount of time, you get a small increase in the population. It might even be less than an individual. And we will do the exact same thing with a human population. In a human population, you might imagine that every individual has, let's say on average, every individual in human population has, I don't know, 2 or 3 offspring. But that's over their whole lifetime. So rather than us having to figure out exactly when every single human has their 2 or 3 offspring, we smear that out over the lifetime of every single human, even humans that if we were to simulate every human individually, maybe someone wouldn't have any offspring. So instead we assume every human is constantly producing fractional humans. And if we have enough of those humans together, then we are going to get the same effect as if we managed to keep track of every single human having whole babies. We're going to have them pour out fractional babies constantly rather than popping out whole babies every whatever, so many years. Does that make sense? Okay. Great. All right, so now our banking timeline for bacteria looks a little bit like this. We've got some bank balance here. So every bacteria has this, as you know, it's how many bacteria we start with. And we are going to refer to that balance as our stock. So our stock is a dynamic variable that changes over time. And that stock, every stock, has associated with it a flow. And the flow, as we'll see, is related to the change in the stock over time. This is saying that at every instant of time, there is going to be this change in how many bacteria you have. And so for every bacteria, you are going to get an increase in bacteria at a rate of 1/W. Now, we need to figure out how much that flow would contribute in our compounding period. And so we're going to multiply this flow by the length of time, the compounding period dt, and that tells us that we are going to get an interest, so new bacteria to add to our stock, of dt divided by w. And so our population is going to start with 1, and it will then next compounding period be 1 plus dt over w. And then each one of those has its own flow. They're both producing 1/W, but the net effect of this one is going to be a full 1/W, but the net effect of this one will be 1/W or dt over w times 1/W. That'll sort of be the flow here because you only have a tiny fraction of bacteria that itself is reproducing. So we're kind of allowing the juvenile bacteria to reproduce even more juvenile bacteria. And so you can then calculate the interest in the same way you did here. You just multiply the stock here. You can multiply that by, for every individual, there's a individual flow. So to figure out the total flow, you just multiply the number in your stock by the flow contribution of everyone in your stock. And then that gets multiplied by the length of time. And that's all that we've done here. You see that this is our stock in this generation, and that stock then got multiplied by 1/W to figure out the flow. And then that whole thing got multiplied by dt. And after you distribute the whole thing out, then this becomes the interest rate in the next interval. And then that goes on. It's exactly the same as our banking example, but we just are now not compounding it every year. We're compounding at every one of these tiny little DTs, and that's generating this interest in bacteria instead of an interest in dollars. And that will approximate by birth rate, at least over long periods of time. This will hopefully follow the same pattern we'd see if we actually had real bacteria producing real offspring, where each bacteria waits a whole W before it pops out a new bacteria. So if we were to plot that out, we'd start out with 1, we get 1 plus dt over W at the next little dt time period, we'd get this expression here at the next time period, and so on and so on and so forth. And so what you can end up seeing is that you get this kind of exponential growth in bacteria, the same way you get an exponential growth in dollars at the bank. And that's exactly what we were kind of looking for here. But we really need tiny DTs for this approximation to actually match the real world approximation. And again, that's because we need to choose a compounding period where we can assume no bacteria will end up actually being able to reproduce during that tiny period, or it'll be very, very, very rare. And that's why we have to focus on what's the time scale of the real system, and that means every W time units, and what's the time scale of the simulation. And the time scale of the simulation, the DT needs to be far, far smaller, like 1/100th at least of the time scale of the real simulation. I'm sorry, of the real system. And so if we were to then, this hopefully sounds familiar from your kind of calculus classes, because all we're really saying is that the stock is like a function over time that you could graph. And that function over time, that if you wanted to take the derivative of that function at any instant of time, that derivative would be identical to if you were to create a tiny little interval around that derivative and measure the slope connecting one point in the function with another point in the function. That would be the same as the derivative there. So this funny flow that we've said here, which I've said is 1/W times the number of bacteria, that flow is just an approximate, it's actually exactly the derivative of this stock. So a mathematical expression for this thing would basically say d stock dt, so like dx dt, d stock dt is equal to the stock times 1/W. So that's effectively what we're simulating here. So I could even write that in case that's helpful. So this is like saying d stock dt is equal to the number currently in the stock times 1/W. And so where this here is stock, this is the S. So this is what we've done in the spreadsheet, is we have effectively solved this equation, but we are not solving it symbolically. If I were to solve this thing symbolically, then I would get something like, S is equal to an exponential raised to T divided by W or something like that. And but instead of solving it symbolically, like you would have done in SOS 211 or in a calculus class you might have taken before this class, we're solving it numerically, which means that we are just going straight to the graph. Normally, we would solve the equation, get a symbolic version of it, and then plot that thing and see what it looks like. We're skipping the middleman and doing straight to the graph. And that's what we get out of the spreadsheet, is it gives us what we would get out of the graph if we had gone straight there. Okay. So, so that is where we left off last time. And so I want to add deaths to this, which is the kind of second problem on that assignment D1. Are there questions about that? And we will get to the spreadsheet implementation in just a second. So we'll go back to seeing how we encode all this in the spreadsheet. But are there basic questions about the argument here? I'll wait a little bit. Okay. All right, looks good so far. All right, so we're about to go into the death rate here. Okay, so I have shown you now, at least for bacteria, how to build a little arithmetic model of bacterial growth that works so long as you can keep track of how many bacteria are at the beginning and the end of these tiny little intervals that I'm calling DT, that Vensim will call time step, and that I think Insight Maker also calls time step, or one of them might actually call it DT. So that's the birth contribution. So what about deaths? Well, we can do the exact same thing. So in deaths, I can tell you that that every bacteria is going to live, and I'll call this, I'll call this L for lifetime. So I'll say L is equal to 3 here. That on average, every bacteria hangs around for 3 time units. So if a time unit is a minute, then like 3 minutes. And so that means that there is going to be, this up here was the inflow of bacteria. So that represents a flow that creates a positive contribution to the stock. This down here is going to be an outflow. So this is a flow that contributes a negatively to the stock. And so in order for us to implement deaths, all we need to do is just add another flow. We don't need to go down to, manually go down to 3 time units and then, manually remove a bunch of bacteria, and then another 3 time units and manually remove a bunch of bacteria. We don't need to do that. At every DT, we just add in the effect of the inflow, which we already have, and the outflow, which subtracts away from it. So at every DT, we're going to adjust our flow to be equal to this expression up here, which will be 1 minus W, which is our inflow, minus 1 over 3. So this here, 1 over 3, you could also call that 1 over L if L is our parameter that's keeping track of the average lifetime of a bacteria. So that you just change the expression so that instead of saying DT over W, you just take this flow expression here and multiply that by DT instead. And then you run the simulation and it works the same way. So that's all I'm kind of summarizing here, is that we're just going to say we've got an inflow, which is going to be however many bacteria we have times their inflow contribution. That gives us the total inflow rate. And then the outflow is however many bacteria we have times their contribution to the outflow, how many bacteria are leaving the system. And so every bacteria is leaving the system at a rate of 1 over 3. So that's the outflow rate. You put both of those things together, and then the net flow is just inflow minus outflow. And every bacteria is going to contribute this much to the net flow of the system. So you're just going to multiply this net flow per bacterium by the current number of bacteria in the current DT time step, and then that whole thing by DT to tell you how much bacteria are going to change in the next DT. And that could actually mean that the number of bacteria will go down or go up. All right, so before I show you that in a spreadsheet, are there questions about that? And just so you see where we're going with this, once we're in Vensim or Insight Maker, then you will be responsible for coming up with the flow rates here. And when you open the Vensim model for the first time, you tell it your DT. But then you forget about the DT and you go through and draw a diagram where you basically go through and you put in all the flow rates. This is my inflow, this is my outflow, and each one of them will have little formulas, just like this formula here. And then when you click run, it will then put together a spreadsheet like the ones you're manually doing here. And then it'll do all this multiplying flows by DTs and calculate how the stocks change over time, and then just give you a graph or a table, and that'll be done. So that's where we're going. Okay. So here it is in the spreadsheet. I see some requests for that. Just shut up, Ted, and move on to the spreadsheet. So so if we start with the spreadsheet, this is going to look just like the, okay, I see a question here. Why is the outflow bacteria times 1, 3? Missing that reasoning. So every bacteria, so I'm going to go back to one step here. Every bacteria, every single bacteria sticks around on average for 3 time units. So every single bacteria is shrinking at a rate of 1/3. And so if we want to measure the total shrinkage of the whole population, then it's the number of bacteria shrinking times how much each individual bacteria is shrinking. And so the number of bacteria times 1/3 gives you the total population shrinking rate, and that's the outflow rate. So that's why the outflow is number of bacteria times 1/3. The lifetime is 3.
I have a question.
Yep.
So if it's bacteria, just because I guess I'm curious why the number is 1/3 instead of say like 1/2 or
It's
1/4.
whatever. I just arbitrarily said, assume that the lifetime is 3 time units.
Oh, gotcha.
Yeah. So
Okay.
it comes from this right here. It's not 1/3, it's like 1/L.
Okay. Thank you.
Yep. Okay, I'm sorry for that confusion. Yeah, just like W is a parameter, L is a parameter, and we'll make that explicit here in the spreadsheet. So what I've done here is I've created a spreadsheet, and I put my DT. This is my compounding period. It's going to be 100th of a minute or 100th of a second, whatever your time unit is. Then I'm going to put W, which is kind of my birth rate. So you could call this a birth rate, I suppose, but it's a birth rate per bacteria. And then you can think, or I don't want to call it a birth rate. So because 1/W is kind of the birth rate. So it is it's kind of like a time between births. Yeah, all right. So W is the time between births, and L is the lifetime or the average lifetime. And so we're just saying here that the bacteria, every bacteria waits about 0.75 time units, let's say 3/4 of a minute, until it produces a new bacteria. And then that new bacteria starts its clock. And then every bacteria, once it's born, on average, hangs around for 3 minutes until it disappears. And so from these W and L's, from the W, I can calculate a birth rate, which is just 1/W. So that's all this is 1/W. And the lifetime here, 1/lifetime gives me a death rate. So this is 1/L, yeah, 1/L, right? And so, and I'll show you the formula for that in the next half of this slide here. Maybe I'll just animate that. So that's all I've done here is I've taken this lifetime and turned it into a death rate. So that shows you that if I give you demographic stats on populations, you can convert lengths of time into rates. And that's going to be really important because when we simulate dynamics, we need to really be thinking in terms of rates. But when we take stats, and I see your hand, Morgan, I'll get it in just a second. When we take stats on populations, it's hard to sort of ask somebody like, what's the death rate of the human population? But you can ask somebody more easily, what's the average lifetime of a human or a human male or a human female in the United States and so on. And we can then turn all these average lifetimes into death rates per individual. And that's just by taking the reciprocal. All right, Morgan, you had a question?
Yeah, it's kind of it might be a dumb question, but what happens or what does it mean when you like say, I know you have $B, $3. What is the $sign to, like, let's say you removed $sign in front of 3, what would you be seeing instead of like the, or vice versa?
Excellent question. Yeah, so this is a good, just an Excel or Google Sheets type of question. So those $signs will not change the calculation of this formula. What these $signs do is they ensure that if I were to copy these cells and paste them somewhere else, then it won't change the B3. See, normally, if I were to copy this green cell here that I'm kind of etching out here with my mouse, if I were to copy this thing to the right, that B3 would turn into a C3 because it was in column B and now it's gone into column C. And so normally what Excel says is, oh, what you want is the cell 1, 2, 3 up from here. And so in order to give you the cell 3 up from here, I'm just going to change the B to a C. Putting the $sign in front of there says, no, I really mean B3. even if I copy this green cell and paste it somewhere next to it, like I could paste it to the cell next to it here, I still want it to be B3. I don't want you to change that. You should always point to this special position here. So does that make sense? Excel always tries to maintain the relative position when you copy formulas around. Putting the dollar signs in front of the column or the row tell it that you want to fix the column, fix the row, or fix both. And that's right, for the number 2. So by putting it on both, I'm saying that I mean this cell, and I'm fixing both. Like this death rate should always be 1 over this cell right here, even if I don't like where these, like I might decide I want these 4 cells just to be moved over to like, you know, this position here. I just don't like them over here. Well, if I copy and paste them over there, if I didn't have those dollar signs, then it would try to put a formula that is referring to cells up here. And so I'm telling it, no, don't use relative formulas, use absolute formulas. Fix both the row and the column so that you're always keeping them here. All right, any other questions about that? I think Oscar, you also mentioned you were wondering about that. Does that make sense now? That it's just, if you're not planning on copying, pasting the formulas or filling down, it doesn't matter. But once we start filling down and copying, then it starts mattering. Okay, great. So speaking of those formulas then, let's then expand our spreadsheet to start into where the simulation actually is happening. And so this is like the second part of assignment D1. And so we need a time column. We always need a time column. We always start at time 0. So that's, you just manually type that in 0. And then underneath the time column, that is the time at the next compounding period, which will always be the previous time plus the DT. So notice that I did not use dollar signs for the previous sign here. I could have put a dollar sign in front of the A, but I didn't there. And it turns out that it can be convenient in this particular case because our formulas are so similar and maybe you want to copy from one column to another. But the idea here is that if I take this formula and I fill it down by grabbing the little square that shows up here and then dragging it down, then it will keep the B1 in this position, but the A9 here is going to change to an A10 down here. It's going to change to an A11 down here and so on. So basically by filling down, what I tell Excel is I want this formula to always be the cell above plus B1. And that's what the dollar signs do, is they make the plus B1 stay while the rest of the cell is always the cell above. Hopefully that makes sense. Does that make sense to everybody, this formula here? And that is just there to allow me to calculate the time at the next DT time step. So then for the rest of this, so I also need to fill in, okay, got you. Yeah, so I also need to fill in manually the number of bacteria, initially 1. And I don't fill in these yet. This one, and this one are all going to be formulas that I were about to put in. So, so yeah, I have this 1 bacteria that I filled in there because I start with 1 bacteria. And notice that this formula just ends up being whatever my DT is, and it'll be 2 times my DT down here. It'll be 0.02 here. So I put in that 1 bacteria there. And then I focus on what's going on in that row. And so I need to go over to the number of births. So now that we're not dealing with a bank, if it was a bank, I'd be generating interest. But I'm not generating interest, I'm generating births. And so this is technically a birth rate, not really births. So I could maybe cross this out and I could call this like a population birth rate, maybe. If that's, makes more sense, because it's not absolute births, it's how many births per unit time. So it's like a population birth rate, whereas this up here, these are like individual birth rates. So these up here are like individual, how many births per individual per unit time. So I'll say per individual. And so this down here is per population. So this is like a death rate and a birth rate per population. And so I get that population birth rate by saying how many individuals are in my population. That's B9. That's the number of bacteria currently at time 0. And I multiply that by the individual level birth rate, which is up here at B5. And that's, I've got dollars in front of it because I always want this to be the individual birth rate in every single cell, even after I fill down. And then I can move over to the deaths, and it's going to be a similar formula where it's just B9, which is again the number of bacteria at our current time step, times the individual level birth rate per unit time. And so this gives me my population level death rate. So I can write population death rate instead of deaths. That's probably a better thing to write. All right, so now I know at the population level, I know how many are in the population. That's the number of bacteria. I know at the population level what the birth rate is during that DT time step. And I know what the death rate is at that DT time step. So I can just multiply the birth rates and the death rates by the duration of time DT, and that will tell me how many absolute births and deaths happened. And I can use that to figure out how many bacteria pop up in my next population. So that is what I'm going to do in the next slide here. But let me get this question. What was the formula for population birth rates again? I can step back one step. And by the way, all these slides are online too. If you'd like to download from Canvas and follow along or take a look at them afterwards, this is in PDF form online. And so the population birth rate is just the number in the population times the individual level birth rate. And there was a question, why did I use a DT of 0.01 instead of a DT of 0.1? So when on Tuesday, when we did a DT of 0.1, I just happened to use 0.1, and the 0.1, like I mentioned on Tuesday, was probably too large because it was too close to the time scale that bacteria are actually reproducing in. And so so that we, DT is smaller than W and DT is smaller than L at 0.1, but it's still kind of like not much smaller. And so because it's on the order of a 1/10 of the actual time scale of the system, there's still a pretty good probability that you're going to get births and deaths within that 1/10 of the time scale of the real system. So it needs to be like 100th of the time scale of the system. And in reality, we are going to, you're going to find that you just have to keep making your DT smaller and smaller until your graphs stop changing. And once you find the kind of largest DT that generates graphs that stay the same for every DT smaller than it, then you stick with that one. And that's something we'll see in just a second. There was a question, are we going to use a value W equal 0.75 in the homework? I think that's what I asked you to do in the homework, was a W of 0.75. And then so there was a question about zeros. Well, yeah, so let's move on in the formula here. So the next formula we need, and then I'll get to these questions, but I want to make sure we get all of our formulas before we fill down. This is a really, really important formula, is that this keeps track of our stock in the next time step. And it is our stock in the current time step plus DT, that's all this is right here, times the inflow rate from the previous time step minus the outflow rate from the previous time step. And so this is the net flow rate here. And so that gives me a population level net flow rate per unit time multiplied by the duration of time we allow it to flow. And then that generates our interest. So that's our interest basically, and that we add to our stock. So that's like our interest being added to our balance, which is right here. This is like our balance or our stock. And so once we have all of those, then you can start filling them down. But note that the numbers aren't going to look right until everything is filled down. So you've got to grab this guy and fill it down. Then you've got to grab this one and fill it down. And then you've got to grab this one and fill it down. And you can grab these two simultaneously and fill them down, by just highlighting both of those and moving down. But be careful, you don't want to go all the way over and also highlight this one, or else you'll obliterate this formula here. So because this formula is in a different row as the other two formulas, you kind of got to fill it down separately. So fill your B column down first, and then fill your C and D columns down. Once you've filled the B, C, and D all down, then you should start to get numbers that look like this one. When you only filled one of them down, you might start to get zeros or something like that. Now there's a question here. Is it okay for our graph for number 1 have a DT of 0.1 and question 2 of graph of 0.01? I don't recall. I need to look at the assignment. If I didn't tell you a DT, if I said just choose a DT, then that's fine, that your DTs are different. But if I told you to use a DT, then you can use them. I recommend, if I've told you to choose a DT, you choose the same DT in both, just to make things easier. There's a question, do we need to have 50 rows? That's an excellent question. You need to have as many rows as you need for this time variable to equal the duration that I asked you for, which I believe was 5. So in order for the time unit to be 5, you may need to have 50 rows, or you may need to have 500 rows. So in this particular case, every row is only 0.01 time units. So in that case, if I want you to simulate 5 time units, so like over here, if I want this to go to 5, I'm going to need 500 rows. So if it was 0.1, I would only need 50 rows. So the size of this DT changes how many rows you need to simulate. And so this was my example here for a DT of 0.01, which means I needed 500 rows to get this full curve. All right, and that actually works really well into the next slide, but I just want to make sure there are questions about that.
So we can just drag it down to make it 5, the time?
That's right. You can drag the time down until it turns into 5, and then you drag everything else down to match that. Or you could drag them down until it's more than that and delete a bunch of rows, or only plot the thing that happens up to 5, either way. Okay, so if your time intervals, so I assume you mean this column here, are saying 0, like let's say, then that might have meant that you grabbed this top column and filled it down. If I go back to where we did the formula for that time column, then you need to make sure that this formula is in the first cell under the 0, and then fill that one down. If you grab the 0 and fill it down, it's just going to copy 0 all the way down through. But if you copy this one and fill it down, this formula and fill it down, then that should populate it properly. If it doesn't, then make sure that up here in your B1, you've put 0.01 and you've not accidentally put 0 there. So I'll go back to this one here. Any other questions about where we are so far? All right, looks like that resolved that question. Great. And let me see if there's any other questions back here. I think I've handled all of that. So let me double check the web in the 212 questions anonymous page, nothing there. Okay. All right, so there's been questions about DT, the effect of changing DT. And in the homework, I asked you to try a couple different values of DT. And so what is the effect of changing DT? So if you were to go through and change your DT, in this case, I did a DT of 0.01 as my baseline, a much smaller DT, 0.001, and a much bigger DT of 1. And in each one of these, I changed the number of rows so that I was making sure that the last time row was 5. If you change your DT, then you'll notice that you'll either simulate way more than 5 or way less than 5. And so you need to change the number of rows to keep it only at 5. So like when the DT is equal to 1, I only need 5 rows. When the DT is equal to 0.001, I might need 5,000 rows. Okay, so what's the difference between changing these? Well, if we look at the DT equal to 1, I'm now simulating one time step 1 minute, for example, per row. And if you notice, this curve has these like very clear corners in it, these little kinks in the curve. And those kinks occur at every time unit. They occur at 0, our initial condition where we had 1 bacteria, and then 1 DT later, and then the next DT later. So what you're seeing here are every DT, but our DTs are so darn large that we can actually see them. And we expect that because our bacteria reproduce every 0.75 time units, this has got to be a bad approximation. We're going to miss reproduction events because our bank analogy assumes that no reproduction events happen during the DT. That means we're going to miss reproduction events. And so if I look here, after 5 time units, I get about 30 some bacteria. But if I look up here and my DT equal to 0.01, after 5 time units, I get like 150 bacteria. So this just goes to show by shifting my DT from 1 to 0.01, I get a lot of those missing reproduction events that I just was averaging over in this case here. So clearly this DT is too large. Now, the question is, without having the physical system in front of you, without asking a microbiologist, what should the population be after 5 minutes? How do I know I've chosen a small enough DT? Well, the idea here is if you keep making your DT smaller, like we do here, eventually you find that your curves stop changing a whole lot. So if I look here at a much smaller DT, then after 5 minutes, I still get basically the same number of bacteria that I get in this other DT over here. It's still roughly about 150. So this curve is a lot less choppy than, or this curve is a lot less choppy than this curve here. And this curve shape, although you can kind of tell it's a little rough, looks a lot more like this curve shape. And they both basically hit all of the same points. So that tells me that it's fine to use a DT of this small. But if I can actually get away with using a bigger DT of DT equal 0.01, and then Excel has to do less work. I have to generate less rows, and it takes less time for the computer to do the simulation. There's a question, is there a way to edit the x-axis tick marks? My x-axis seems to be going every point. And yeah, there are, and I can do a quick, I'll bring up Excel here and do, I'm not going to do the whole simulation here, but I'm just going to show you where to find graph stuff. So let me bring up an Excel sheet here. And again, I'm not going to do the whole simulation, but if I were to pretend like this was my time column and this was my bacteria column, so 1, 2, 4, 8, etc. If I wanted to plot this thing, I might highlight this thing here. I might go to insert. I might look at the recommended chart, see if there's anything that I like there. Maybe I like this one. I am going to go with the scatter plot here. And so now I say, okay, I see all the points there, but I want to be able to edit these things. So at least in Excel, and there's similar things you can do in Google Sheets, if you click on this, then up here under add chart element, this is under chart design. See up here where it says chart design. If I click on the chart, I'll get a chart design. And then over here, there are a bunch of things that I can do. Like I can say add chart element. And if I want, for example, I could add an axis title. And so I can say primary horizontal, and I could put time in there. And I can then go back to the home ribbon to change the font and things like that. And so so if you're looking for, if you want to add anything, go to this guy and you can find all the stuff you want to add. Now, if you want to edit the ticks and things like that, if you click on the chart here, there is a, I think under format, if I go to the format up here and then go to format pane over here, then if I click on different elements of the chart, it gives me different options that I can change here. So under like chart options, I can change all that, these are graphical properties. I can, if I click on the actual ticks here, then it gives me, under this little thing that looks like a bar chart, the option to change, what my minimum and maximum is, my major and minor units. On the ticks, it tells me whether I want, tick marks and where I want the tick marks. So maybe I want this to only go to 5 and so on. So the idea here, you click on whatever chart element you want, and once it highlights, you can look for these chart options, and then you can adjust these things like, where you want the lines to be drawn, how far, etc. And the y-axis here, I'd say if I went into chart design, I could say add chart element, and on the y-axis, primary vertical, I might put, number of bacteria or something. Something like that, number of bacteria in population. Now that's very small to read. I could click on this thing and go to home, and then I could increase the font size. And so on. So hopefully that makes sense. All right, so if anybody else has any other questions about where to find things in Excel, feel free to ask. I'm gonna take a look here at the chat. Is there a way to edit the x-axis tick marks? Okay, I think we covered that. We have, so the graph is the number of bacteria on the y-axis and the times on the x-axis. That's right, this behavior over time plot plots number of bacteria on the y and time on the x. With our graphs, we want a 5 time unit period. So yeah, you want your graphs here, and let's see if I were to click on this guy, I can also increase those tick mark sizes, and I want this to go to 5. So if yours only goes to 1, you probably need to simulate more rows, or you need to change which data you're plotting. So if you click on the chart, there is a, if I right click on the chart, there is a select data, and I can go under that, and then I can see what it's plotting for my data types here. So it says chart data range, and I can select a new data range to make sure I'm selecting my whole 5-minute simulation. Okay, any other questions about how to get these things graphed?
If it's going from, my graph is going on the y-axis from 0 to 160 instead of say 0 to, I think that's 95 on yours. Is that a problem?
Well, if we,
oh wait, we're not looking at the same data. That's why it's happening. Never mind.
That's right. That's right.
Never
I'll
mind.
move this away. If yours is going to 160, that's good.
Okay, thanks. Appreciate it.
All right. Any other questions about the Excel stuff? Okay. And Rachel, I hope I answered your question. That my graphs were for a 5-minute period. That's, or yeah. Okay, great. All right. So, and I hope this DT makes a little bit of sense here to sort of summarize up. Yeah, Claire, go ahead. Elise, the equation for births. So that's, if I were to go back and look at the
I'll just talk, sorry, it was a little quicker.
oh yeah, it sounds like we had some feedback there. And so if I can go back to this is the births equation here, which is just the number of bacteria times the birth rate per bacteria per unit time, so that together this is the birth rate per unit time for the whole population.
Oh, so it's so it's what is it? B9 is, so the initial population times birth rate?
Birth rate per individual. So it's basically the current population, which in this first row happens to be the initial. So it's the current population times the birth rate per individual.
Birth rate per individual is 1 over 0.75.
That's right.
Oh, okay, that explains it. Thank you so much.
Mm-hmm. Okay, any other questions?
Again, for the time, you know how it does the point, it'll do the point. How did you do it where it was like the whole numbers? Or does it matter? Because for mine, I'm seeing the time that says 0.2, 0.4, 0.6. That's how it's supposed to be.
I'm okay with that. I just, you know, it's kind of, these are sort of stylistic things. If you don't manually edit these things, if you drag the graph larger, like wider and narrower and taller, it's going to change those automatically for you. If you really want to force them, then that's, if I were to go back to my Excel example here, you can click on the axis that you want to change and wait for all the numbers to get highlighted. Go into your format menu up here, make sure your format pane is up, which is this thing here. And then under the axis options here, click on the thing that looks like a bar plot. And you'll be able to see that it says like major units 1. If I change that to like 0.25, then I can see that it puts in a mark at every 0.25. Now that's pretty ugly for this width here, so I can make this a little bit wider and maybe it looks a little bit better. But if you don't manually change that, then it tries to make a good choice for you based on the width of the graph. And if you want to go back to that automatic, you can click this little reset, and then if I drag this thing around, it will change that. Okay, any other questions? So that's great. We've done our first population simulation. And the mysterious thing here is, again, how do we set that DT? And the kind of guidelines here is that you try different DTs and you want to choose the smallest DT possible that makes it so that your graph stops changing. So if you try really large DTs, then as you make the DT smaller and smaller and smaller, then your graph will keep changing more and more. But eventually you're going to get to a DT that is so small that if you keep making it smaller, your graphs don't change very much. And you need to find, once you've hit that point, you don't need to make your DTs any smaller. You can leave them at that DT that you found. Because if you make them smaller, it's just going to make the computer do more work, but it's not going to actually make your simulation any better. Okay. So are there questions about that?
I had a quick question also. You know how it goes in increments of 0.1 or 1 to 1.5 to 2 in 0.5 increments? How do you change that? Because mine's going from 1 to 2 to 3 to 4 to 5 and then ending at 6.
Yeah, oh, right. So that was, and I was actually flipping slides behind there, but I forgot that I was, I'm looking at the wrong screen. So yeah, this here, if you click on that so that you manage to get, it might take a couple of clicks, but you got to click on the numbers. So you get a box around the whole numbers. Then you go up to format, you make sure your format pane is turned on, and that will turn on this thing on the right. Then under axis options, you can click on the thing that looks like a bar chart. And then under this axis options, you can change the minimum and maximum. So if you don't want it to go to 6, you can manually force it to only go to 5. Likewise, if you don't like where it's putting the intermediate, where it's putting the major tick marks, you can change the major units here. And this is the space between the major tick marks. The little minor ticks here, this is the space between them here. So you have control of all of that right here under the little bar chart tab in the format pane, but you have to click on the actual axes first.
Okay, I got it. Thank you.
Mm-hmm. All right. And so the slides that I was going through there, well, really it was just one slide. And it was just, again, this DT thing. Too large of a DT and your simulation is inaccurate, but fast. There's a speed accuracy trade-off here. Too small of a DT and your Excel spreadsheet will take forever to calculate, and it requires you to run a whole lot of rows, and you end up not really getting anything better than a slightly larger DT. So you may not have ever thought about your Excel spreadsheets running slow, but if you start working with data sets or simulations that require thousands and thousands of lines in Excel, you'll notice that as you start changing things, it actually takes a while for Excel to like update all its numbers. So you really want to use as few rows as possible, but while still getting an accurate simulation. So any other questions? We've basically done all of that assignment D1, including the DT part. You just have to replicate that by yourself. And some of you, it sounds like, have been doing it behind the scenes. All right. Okay, so the big picture here is that the bacteria you've been simulating is our stock. And the birth inflow is like this flow rate here, and we are gradually learning how to build these things. And so I've taught you how to put a stock column and a flow column, two flow columns, an inflow and an outflow, into your spreadsheet. And when we go into VinSim, you're going to put the same formulas in VinSim. You're just not going to put them in columns. You're going to drill down into this little variable called flow and this variable called stock. And this will be where you put your initial number of bacteria. And this is where you'll put the number of births going into the bacteria. So this will be where you put your number of bacteria times birth rate per bacteria. And this diagram here is not only equivalent to your spreadsheet, where, by the way, the DT isn't shown in the diagram, but it will be behind the scenes. You'll have to tell VinSim what DT you want. This whole thing is identical to this calculus expression here. And so, which is also identical to this, this calculus expression, this integral here. And so the graph that we got out of Excel would be the same graph you would get if you were to solve this integral, where this flow would be your number of bacteria. So this, this would be your number of bacteria times the bacterial birth rate. Then this here, if you were to integrate that thing, would end up giving you a expression that if you plotted would give you the exact same expression that you end up seeing in your Excel plots, so that you did in Excel. So we're just jumping straight to the graph. Okay, so this is the way it would look if we actually went through and modeled the bacteria in VinSim. So this is the mathematics of it down here. This is like something you might see in a calculus class. We aren't, doing it the mathematical way, we're doing it the numerical way. So we were going to draw, and we'll learn how to do this starting next week. We are going to draw stock variables, which are these boxes. We are going to draw flow variables, which are these arrows, these thick arrows. The box here is exactly like this column, number of bacteria. The arrows are exactly like these columns, births and deaths. And the extra things that we use up here to help us with the calculations are these converters, which are depicted up here. And they just make the math simpler inside these formulas here. And so this diagram, when I hit run in VinSim, generates an output, which is depicted in the little graph here, which is identical to the output that you get inside Excel when you just let this thing run and then plot these two columns here. So that's what we're working up to. Okay, so any questions on that? And we are going to learn how to do that in VinSim next week. All right.
I have a question.
Yep.
So you're saying next week is when we would like incorporate those converters of like not time and number of bacteria, but now we're going to insert like the birth and death data is kind of what, or is that what we're learning this weekend with our homework assignment?
Well, the homework assignment stays in Excel. Next week, that's when we throw away Excel and we learn how to do this all in VinSim. And so, so next week is when we're going to learn how to build a diagram like this one, which ends up doing the same thing you do in the spreadsheet. But it ends up being a lot easier to make to edit. Like if you wanted to add a death, like if we started out with just births and added deaths, it's really a pain to do that inside Excel, to keep adding like new columns and updating all these formulas. So it's a lot easier to do that as a diagram, because I can just draw a death flow, and then Vinsim is going to do all of the spreadsheet updating for me in the background. So that's what we'll learn how to do next week.
Okay, so basically the whole point of like doing the C9 minus D9 is so that you can incorporate the like other portion of the data into the graph per se.
You mean the whole reason the whole reason we're using the spreadsheet here is just to show how things were done before programs like Vinsim existed.
Oh, okay.
So yeah, so once upon a time, this thing that you're doing in the spreadsheet, this is how we did simulation, is that we had to come up with all these formulas in all these different cells and fill them all down and plot them and do that all manually. And when we needed to update something that we might draw out on paper, we'd have to update all these formulas in the spreadsheet. But now we have programs like Vinsim and Insight Maker that allow us to draw the diagram in the computer, and then the computer does the translation step for us. So we only have to work with the diagrams. We don't have to worry about all the formulas behind the scenes.
Very nice. Okay, thank you so much.
Mm-hmm. Great questions. Any other questions? All right. So now that you've learned how to do this bacterial example, let's then make it a little more exciting. And this is your assignment D2, where in the spreadsheet, you're going to simulate a system which is similar in complexity as the bacteria, but is a very different system. So the bacteria ends up being a growth process. Now we're going to simulate a toilet, which is a balancing feedback loop. And so the idea here is that we are simulating what happens after a toilet is flushed and starts refilling. So it's an empty tank, and we are simulating the trajectory of the water as it comes into the toilet and eventually settles down and levels out at a particular level. So we are assuming that a toilet tank at water level is initially 0 centimeters high. It has a target water level of 15 centimeters, and the flow at any time is going to just be 15 centimeters minus the water level. So in the past, our flow was like number of bacteria divided by W. Now there's no population involved. Our flow is just going to be this expression. It's going to be 15 minus whatever the level is. There's no multiplied by the level or anything like that. So this here ends up being the expression that you'll end up putting into the spreadsheet. And then that expression will get multiplied by dt in order to find the water level at the next time step. So with these assumptions, you build a simulation of the toilet, and I'll show you a diagram, and so I'll give you more details here in a second, where you're going to have to choose a sufficiently small dt to ensure that you get a good simulation. And just so you know, the final simulation you get should look something like this, where it will start at 0 and it will then rise up to 15. And it'll get closer and closer to 15 without actually hitting 15. So you should show at least 5 seconds. And so you should again plot until 5 time units, and you get this kind of exponential, or this kind of damped exponential where it rises fast and then levels out. And then we need to show your plot embedded within a Microsoft Word doc. I want you to submit your spreadsheet, but your main results are in that Word doc. So I don't want Eric to have to grade, thousands of rows of a spreadsheet. I want him to sort of see your final results in the Word doc. And then the spreadsheet is only there to debug things if things look a little bit odd, and to kind of see how you did your work if we need to see that. And so there's a question: if 50 rows are 5 minutes, then how many rows are 5 seconds? So it all depends on what your DT is here. So if your time unit is in units of seconds, and so if the whole spreadsheet is in units of seconds, then if you've got a 0.1 DT, then you need 50 rows. If you have a 0.01 DT, you need 500 rows. If you have a 0.001, you need 5,000. And so when you start basically just fill that time column down until you have enough rows for the time column to equal your final time. And let me just make sure we get through the rest here, and then I'll make sure we get to these questions here. So you're not only going to do this thing in the spreadsheet, but I want you to draw a complete causal loop diagram showing me the water level, the target water level, and the flow. And I'll kind of give you a hint for that in a second. And then for extra credit, you can add a leak, which is similar to adding depths. So just as a reminder, this is basically the CLD that we're working with here. We've got a target water level, which is like our goal. We've got our water flow, which is like our action. And we've got our water level down here. So this is our H2O level. And as the target water level is increased, that's going to increase the flow. But then likewise, as the water level decreases, that's going to increase the flow. And so that's what gives us this balancing feedback loop. So as you increase the flow, it's going to increase the water level. So this is what we're simulating here. And so I'm just showing that here, that this is our flow and that is our stock. This is effectively the CLD that you'll be submitting for this assignment. And what are the formulas then that you'll need to put into your spreadsheet? Well, I'm giving you the formulas here. Like, this is what you'll put in your flow column, and this is the stock that you're worried about. So remember that every the next L is just going to be the previous L plus the flow times dt. This will be what's in the cell underneath every water level. It'll be the previous water level plus whatever's in your flow column times dt. And this here, 15 minus the current water level, that will be what's in your flow column. So just as a reminder, you can use a template like this one, where your stock here might be your water level L, your flow here might be 15 minus L. And then you just work down through that. And so you'll be able to, then say, well, okay, if this is my initial water level 0, then this is going to be the previous water level. So, B3, plus whatever my flow is here, whatever this cell is, which will just be 15 minus B3. And then it'll be whatever that cell is times that D, so this is supposed to go to that little dot, times the DT, which is above. So this cell up here, just make sure you use the dollar signs. So I'll just put a dollar sign there. So it's a little scratchy there, but that's basically the solution that you're going to end up getting for this water level thing. All right, so just want to finish the announcements here, because I'm happy to take questions, because that's all I've got for you. Again, keep reading chapter 3. On Thursday of next week, that's when the chapter is due. So the perusal assignment, the reading exercise, and the reading assessment are all out there. Then you'll read about Moorcroft introducing you to stock and flow diagrams. Basically everything that we've talked about here so far, maybe with a little less detail. So hopefully they'll be complementary. As I mentioned last time, start thinking about who you want to do a final project with. You will basically, the Saturday after, you basically have a week after the midterm, well, not quite a week after the week after the first midterm, stage 1 of the midterm, to say who's going to be in your team. And then something like a week after that to give roughly an idea of what system you're going to try to simulate. So, and then I can put some things on Canvas to help you guys form teams if you're having trouble forming teams. But otherwise, I recommend posting the discussions, posting the Slack. Feel free to use the @channel to send a broadcast to everybody on Slack, so that you can, say that you're looking for a teammate or you're looking for teammates. Try to get 3 or 4 people on a team. Create an Insight Maker account so we can use it next week. And then the assignments due this Sunday. The D1 and D2, these are kind of like a combined assignment. I've already done D1 sort of for you and given you most of the formulas for D2 and then the muddiest point. Okay, and everybody in the class should be on the Slack. Click on the Slack link on Canvas on the left-hand side, and then you'll be able to get onto Slack. So if you go onto Canvas, look on the left-hand side nav bar, and there's a link to the Slack site. All right, so you know, there's the midterm stuff. Again, I won't get into detail here just yet. I'll talk about more about this next week, but it's a two-stage midterm. I'll kind of give some details about that. I want to give you guys your attendance exercise, and then I'm happy to stick around a little bit for questions, and I have office hours today anyway. And so of course, if you'd like additional help, feel free to come to my office hours room. So the question I have here today is what is the okay, what type of feedback loop is the toilet tank? Is it balancing or reinforcing? Or if you like, negative or positive? So the toilet tank, again, it starts out empty and it eventually reaches a point and then stops. And so the difference between the target and the actual water level gets smaller and smaller and smaller over time until it goes to zero. So does that represent a reinforcing loop or a balancing loop? That is your attendance question. And that's all I got for you today. Happy to take questions and stick around here for a little bit. Otherwise, I will flip in a few minutes to my office hours room, and you can feel free to stop by there as well. And thanks for your patience with the Excel. All right, looks like we're getting a kind of anti-quorum here.
I had
Oh, yep.
sorry.
Go ahead.
So you said on the Microsoft Word document that we upload as like in addition to the Excel document, on the Microsoft Word document, I could probably read through the instructions, of course, to answer this question, but you wanted us to just like give the scatter plot graph or like the line graph instead of like all those values, I'm assuming, right?
Right. So in the Word doc, we have to sort of imagine like if you were asked to generate a simulation at the office or something like that, then they probably wouldn't want to see the table of values. We want to see it depicted graphically. So kind of view that as like your opportunity to practice depicting these quantitative results graphically. And the best way to do that is in a graph as opposed to just dumping all the numbers.
Okay, yeah, I saw a plot and I was just like, does that mean graph? And it does. So thanks.
Yes, that's right. Okay. Anything else? All right, I'll double check if there's any questions hiding in the, all right. Okay, in that case, have a good weekend for anybody I don't see in office hours.